All right. This is my second attempt at recording this, so thank you for being patient with me. Let's start by defining how do we add fractions. So if I have 5 over x minus 1 plus 3 over x plus 2, how do we add these fractions? Well, one, they're not the same denominator. So our first step should be to get them to the same denominator. And we can do that by using the denominator on one of the fractions and multiplying it on both the top and the bottom of the other fraction. So if, for this case, we can multiply x plus 2 over x plus 2, and because they're the same, it technically equals 1, multiplied by 5 over x minus 1. And vice versa. We can do 3 over x plus 2 times x minus 1 over x minus 1. This works great so far. And now we just have to simplify, and we get, quick math, I got 8x minus or plus 7 all over x squared plus x minus 2. So that's how you add fractions with that's how you add fractions just in general. What partial fraction decomposition wants us to do is to do this process backwards. And this process is a little bit more difficult than adding it. So how do we start to add these fractions or to decompose these fractions? Well, first, we should worry about the bottom. We can see that if we can break up the bottom, we can get it back into the two original linear equations that it were in, x minus 1 and x plus 2. So this is equivalent to ax plus 7 all over x minus 1, x plus 2. Now, we know that since we're multiplying these together, that we can separate these like we did over here. So we have x minus 1 over something, we'll call that variable a, plus x plus 2 over some variable b, we'll call it b. And now in exactly the fashion that we would multiply both sides by the opposite denominator, we can do the same thing when we decompose the fractions. So we can multiply the a by x plus 2 and the b by x minus 1. And what that gets us is the denominators are now the same. So if I rewrite this, we have a times x plus 2 over x minus 1, x plus 2, plus b times x minus 1, x minus 1, x plus 2. What this gets us now is that now all of the denominators are the same on both sides of the equation. And that's effectively the same as just canceling them out. So we can rewrite this entire equation just in terms of the numerators. X plus 7, 8x plus 7 is equal to a times x plus 2 plus b times x minus 1. And now we just have to solve for the variables. To do this, we could just plug in cases. And the most obvious of cases is to plug in when is x equal to 0 on either side. That way we cancel out one of the variables, and then we can just solve for one at a time. So if we take let's assume x is equal to negative 2 for this case. Because if x is equal to negative 2, this a term becomes a times negative 2 plus 2, which is a times 0, which is just 0. So if x is equal to negative 2, then we have 8 times negative 2 plus 7 equals b times negative 2 minus 1. This gets us negative 16 plus 7 is equal to negative 3, which is, or negative 3 times b. Negative 9 over negative 3 is equal to b. which is equal to just 3. So there's one of our variables, and we can see that that matches up with this term perfectly. Now we just have to do the same for a. We know that b is equal to, or x minus 1 cancels out to 0 if x is equal to 1. So we can plug in x is equal to 1. And if we do that, we get 8 times 1 plus 7 is equal to a times 1 plus 3. We get 15 is equal to a. Oh, sorry, this is a 2. A times 3. A is equal to 5. Which again matches exactly up with what we had earlier. So this is the general process if you have a polynomial on the denominator that is at most a power of 2. Let's assume you don't have something, or you don't have a denominator that is of power 2. In that case, there is a separate process that you want to go through. Let's take this one, for example. X squared plus 9 all over x squared minus 1 times x squared plus 4. Now, obviously, we have to separate some of the fractions, but now we have to worry whether or not that is a possibility in all real numbers. Because let's take this x squared plus 4. No matter what integer we plug in there, whether it be positive or negative, the square of any number will always be positive. Thus, we get x squared is equal to negative 4, which has no real possibilities. So that term is going to have to stay. What about this second term? X squared minus 1. This is the same as saying x squared minus 1 squared, which is equal to x plus 1 times x minus 1. So now we have 3 terms that we have to evaluate. We can rewrite this as a over x plus 1 plus b over x minus 1 plus something over x squared plus 4. Now, instead of just putting a constant here, because we have a squared term here, we're going to have to raise the power up by 1. So now we're going to have some constant c times x plus a constant d. And now the process is very, very similar to what we did with a power 2 polynomial. We can multiply each of these sides by what they're missing. So we can multiply it by x plus 1, x minus 1, x squared plus 4, all over x plus 1. Obviously, it's going to be different for each of them. So for this one, in this case, this already has the x plus 1 term, so we're just multiplying it by the x minus 1 and the x squared plus 4 term. So rewriting this entire thing out, we get a times x minus 1 times x squared plus 4 plus b. It already has the x minus 1 term, so we just have to do the x plus 1 term and the x squared plus 4 term plus cx plus d times x plus 1 times x minus 1. This is very, very intimidating, but through a couple cases, we can get it down pretty fast. So obviously, when is x plus 1 equal to 0? When x is equal to negative 1. So that'll be our first case. If x is equal to negative 1, then we get negative 1 squared plus 9. The a term cancels out, so we get 0 plus b. Oh, sorry. No, we get a times negative 1 minus 1 times negative 1 squared plus 4 plus the b term cancels out, and the cx plus d term cancels out, because they both have x plus 1 in it. So now we're left with positive 1 plus 9 is equal to a times negative 2 times 5. We get 10 is equal to a times negative 10. A is equal to negative 1. So we can go ahead and plug that in up here. And then I can erase the rest of this. What about this second term, the x minus 1 term? Let's assume if x is equal to 1, because then 1 minus 1 is 0, then we get 1 squared plus 9 is equal to, the a term goes away, then we get b times 1 plus 1 plus 1 squared plus 4. And then the c and d term cancel out as well, because they also have the x minus 1 term in it. So from this, we get 10 is equal to b times 2 times 5. B is equal to 1. We can plug that in here. So now we've exhausted all of our real options, right? We've used the x plus 1, we've used the x minus 1, and now we're stuck with this term that doesn't cross the x-intercept, nor does it have a single variable on the top. So what can we do here? Well, we know the value of a. A is equal to negative 1, right? So I can actually just replace a with negative 1 and b with positive 1. And now we can get this d term if we set x equals to 0, because then the c term cancels out, but the d term does not. So we'll have case 3. If x is equal to 0, then we get 0 plus 9 is equal to negative 1 times negative 1 times 4 plus 1 times 1 times 4 plus 0 plus d times 1 times negative 1. This gives us 9 equals 4 plus 4 minus d. Is that right? Yeah, that should be right. Looks like it. So we get 9 equals 8 minus d. 9 minus 8 is equal to negative d. D is equal to negative 1. So we could plug that in up here, that d is equal to negative 1. So now finally we're left with this c. And we've exhausted the x equals 0 option, negative 1, the positive 1. So our best case is just, now that we have all variables except for 1, just to put in the next best thing, let's say x equals 2, and solve for c as if we would normally. So we get 2 squared plus 9 is equal to negative 1 times 2 minus 1 plus 4 plus 4 plus 1 times 3 times 4 plus 4 plus c times x minus 1 plus 3 plus 1, or times 3 times 1. So now we get 13 is equal to negative 1 times 1 times 8 is negative 8, plus 1 times 3 times 8, which is 24, plus cx minus 1 times 3. We could simplify these integers over here, and we get 13 is equal to, that looks to be 16, plus cx minus 1 times 3. Then we get negative 3 is equal to 3 times cx minus 1. We get negative 1 is equal to cx minus 1. Cx is equal to 0. X is equal to 0. Or C. Oops. X should have been 2. Let me fix that real quick. Times 2. C times 2. C times 2. C times 2. Either way, we get C is equal to 0. And now, plugging this all in, we can get our final answer. I'll go ahead and erase the rest of this. We get negative 1 over x plus 1 plus 1 over x minus 1 plus negative 1 over x squared plus 4. And now when you do the integration, you just have to integrate it. Most of them, at least the linear denominators, will be natural logarithms, and the ones with squared terms should just be to the negative 1th power. Other than that, this is really how you do it. There is one special case that you may need to be wary of. If you have a growing term, like let's say 3x plus 4 all over x minus 1 squared. If you have something like this, when you separate it, you can't just do x minus 1, x minus 1. You have to grow the power. So what I mean by that is this first term will be, as normal, x minus 1. But your second term will be x minus 1 squared. This will just be over a regular constant if you are growing the power like this. But just be wary that you cannot start with this. You have to grow the power first. Other than that, the integration should be the easy part of this. It is the partial fractions where specific cases are made that you may need a little bit of help with. I hope this helps explain a little bit of it. Other than that, just DM me if you need any more help.